Hi, it's great to welcome Tim Hsieh from MIT. Tim graduated from CMU very recently, and then he's been a postdoc at MIT for this year. He's been doing some amazing work on a lot of topics, including things around expansion and sort of new constructions of expanders, and coding theory. And he's also done a lot of work on sum of squares and kind of the low degree conjecture and both consequences of it and refuting it, or like at least sort of counter examples to it. And yeah, today he'll tell us about much simpler construction of epsilon balance codes using expander walks or free expander walks.
Okay, thank you so much for the introduction, and also thank you for inviting me here. Today I'll be talking about constructing epsilon balance codes. Okay, let me first start with the basic definition of binary codes. Error correcting code is just an encoding procedure that takes a message and encoding it into a larger code word. So here we're taking k symbols of the message, and then we're encoding it, transforming it into a larger code word by adding some redundancy. And the hope is that this redundancy will give us better error tolerance. In the case when the code words are binary, or 0, 1, then we call this a binary code. Often we view a binary code as just a subset of vectors in 0, 1 to the n. So we think of this as we have a space 0, 1 to the n, I'm just drawing a circle here, and then we're picking a few vectors in this space. And these vectors consist of our binary code. Now there are two main parameters of a code. The first one is the rate. This is defined to be k over n, which equals log c over n. This is a number between 0 and 1, and it tells us how large our code word needs to be. So we want this rate to be the larger the better, because then if you look at here, for larger rate means smaller n, which means we're using fewer bits to encode a message. So it's more efficient. The second parameter is the distance. This is defined to be the minimum distance between any pair of code words. Again, we want this to be the larger the better, because if every pair of code words are far apart, then an adversary can corrupt a lot of entries, and we will still be able to decode to the unique code word. So both of these parameters, we want them to be as large as possible, but of course, we cannot get the best of both worlds. There is some trade-off here, and that's actually probably the most fundamental problem in coding theory, this rate-distance trade-off. So a lot of people have studied this, and this graph appears in most textbooks and lecture notes. Here, we're looking at relative distance, so you can see that this is distance divided by the length of the code word, so it's something between 0 and 1. And actually, we're focusing on the case where relative distance is below half. And it's a simple exercise to show that for binary codes, if the distance is larger than half, then we must have vanishing rate. So that's why we focus only on the case when the distance is smaller than half. In this talk, I will be focusing on the large distance regime. So this regime here just means the distance is 1 minus epsilon over 2 for some small epsilon. Okay, now this leads to the next definition called epsilon balance codes. So a binary code is epsilon balanced if every pair of code words has distance between 1 minus epsilon over 2 and 1 plus epsilon over 2. So technically, if we only want good decoding properties, we only need a lower bound. But for many other applications, we also need this upper bound of 1 plus epsilon over 2. And we're going to restrict our attention to linear codes. So these are codes where if you add two code words up, mod 2, or in F2, then it also is a code word. And we know that in this case, we care about the distance of the code is exactly equal to the non-zero weight of the code word. So here, in this case, we want the weight to be between 1 plus or minus epsilon over 2. So the question is, how large can the size of C be? And in coding theory terms, it will be how large can the rate be in terms of epsilon? Okay, so that's the definition of epsilon balanced codes. And let me tell you about some known bounds on the rate. First of all, we have an upper bound. This is a famous result in the 1977. So we know that the rate must be at most epsilon squared times log 1 over epsilon. Notice this is a result on the upper bound of the rate. So in other words, it's a lower bound on how large the covert needs to be to get the large distance. There's also a lower bound. This is an existential result. This result says that a random code achieves rate epsilon squared. This is often called the Gilbert Varshamov bound or the GV bound. It's a lower bound because it says that there exists a code with large distance and a rate epsilon squared. So you can see the upper and lower bounds here are
Just a
pretty
question,
close.
Usually this is the form of the GV bound, but actually does the construction even have fixed constants in front of epsilon square? I don't remember, but
I think for random code, oh, you mean what constant is in?
yeah, I mean,
In front of epsilon
So, does the actual bound come with some sort of very specific expression which gives a constant? Or
Yeah, so I think people have really tried optimizing the upper bound. So I think there's the best upper constant in the upper bound.
Oh, the upper bound. Okay.
I think the random code, as far as I'm sure there's also a constant, but I don't know off the top of my head.
Okay, but it's not that there's like a well-known precise constant. What we usually know is sort of theta or like omega of epsilon.
Yeah, I think so.
Okay.
Though I think in the upper bound case, I was talking to Venkat,
Uh-huh.
and I was telling him of a new proof of this, and then he told me, does this get constant too? So I think people do care about,
So people,
care about constants here. But I think really the log 1 over epsilon is the main factor here.
okay. Also, you also have a new proof of the upper bound, you're saying?
No, okay, turns out I think it's folklore. Yeah.
Okay.
There are many proofs of the upper bounds, like using this bound is first proved using linear programming, and then you can prove it also using like walks on a KD graph.
Uh-huh.
There are many different proofs. Yeah, so actually this closing this gap is already an interesting problem. There's only a log 1 over epsilon gap here. But today I'll talk about explicit construction. So here the lower bound here is a random code. And random codes are great. It matches GB. But the problem is it uses too much randomness. So in many applications, for example, like pseudo randomness or algorithm designs, we want deterministic constructions. This leads to the question of, can we have explicit constructions with rate close to epsilon squared? And when I say explicit construction, I mean deterministically compute the encoder in poly n time. Okay, so explicit construction will be the focus of our talk today. Let me tell you some known constructions. First of all, this is a very standard method of constructing such codes. So you first take a code with large alphabet, and then you encode each symbol using a small binary code. This method is called concatenation. It's been used a lot. This gives a rate of epsilon cubed. You can see it gives us something, but it's not the GV bound. It's off by an epsilon factor. There's a completely different construction using expander walks. This will be the focus of the talk today. I'll explain what this means later. This is often attributed to Rosenman-Vigerson, and the rate is epsilon to the 4. It's actually worse than the concatenation rate, but the cool thing about this result is that in 2017, Tashma used this framework of expander walk and somehow sparsified it to get epsilon to the 2 plus little of 1. And here the epsilon to the little of 1 is this, to be precise, this is e to the negative root log 1 over epsilon. He actually got log 1 over epsilon to the 2/3, and then very recently Cohen improved it to root log. But it's basically the same construction. And here, you should just think of this little of 1 as being it goes to 0 as epsilon goes to 0. And here's a short summary of what Tashma did. It's basically just sparsifying expander walks using something called the S-White replacement product. So today I will not talk about this replacement product at all. And their analysis is a little bit complicated. Instead, I'll talk about our new construction, which also gets this epsilon to the 2 plus little of 1 rate. And arguably, it's a much simpler construction. So here's a 2-line summary. Here, instead of doing expander walks, we walk on different graphs. And we also, we think that is a much simpler construction, also much simpler analysis. One drawback is that this term is a bit worse, so we don't beat the current best bound. Here this epsilon to the little of 1 is e to the negative log 1 over epsilon over poly log 1 over epsilon. So it's still little of 1, but it's not better than the current best. Okay, any questions? So the next part of the talk will be, I'll tell you about a general framework of construction using distance amplification. The general idea is that we start with a base code C0, which is in F2 to the n. And then we assume that it has constant distance and constant rate. So here we don't assume that it's optimal, it's just some constants. What are we going to do? So we take a vector in C0. This is some x1 to xn. And then we just enlarge this code word into a new code word, and where each entry is the sum of the entries of the original code. Okay, here I'm using the summation in F2. If you want, you can think of this as 0, 1, and then adding would be addition mod 2. That's the procedure of what we're trying to do. This can be represented using a hypergraph. Here we have a hypergraph on n vertices. Every hyperedge corresponds to one entry of the new code word. So for example, the first entry of the new code word is x1, x3 plus x7. This is represented by this red hyperedge here. The idea is that if we choose a suitable hypergraph, then we can somehow boost or amplify the distance of the base code. Remember, we are only assuming distance is some constant, maybe like 0.1. Perhaps this hypergraph somehow amplifies the distance to all the way to something close to half. And of course, how we choose this hypergraph is the key innovation. And before we go on, I want to make a notation switch for this talk. This is actually very often used in analysis. It'll make our analysis much simpler. I'm going to switch F2 into plus minus 1. And from after this, everything is plus minus 1. So 0 gets mapped to 1. 1 gets mapped to negative 1. And then addition in F2 becomes multiplication in plus minus 1. This is because if you add 1 in F2, this is flipping a bit. Then multiplying by negative 1 does the same thing. So in the previous picture, now we have a vector in plus minus 1. And our new code word will have every entry being a product of entries in the original code. Okay, and now if we have weight 1 plus or minus epsilon over 2, then this becomes bias, which is defined to be the expectation over the entries, which is at most epsilon. This is roughly saying that if originally you have roughly half zeros, half ones, then when we switch to plus minus 1, you average them, it's close to 0. So the problem of distance amplification becomes, or is equivalent to bias reduction in plus minus 1. Okay, this is a very standard switch from 0, 1 to plus minus 1. And so from now on, I'll only talk about plus minus 1, and I'll talk about bias reduction. Here, okay. So we have a base code, now it's in plus minus 1, bias epsilon naught, rate r naught, they're both some constants. We're going to choose a hypergraph on n vertices and m hyperedges. The new Colbert will have length m, and this is just the number of hyperedges in the hypergraph. Notice that in this procedure, we're not introducing new Colberts. We're taking the original Colbert and then enlarging it. So the number of Colberts stay the same, but the new rate will be R0 times n over m, because we're enlarging the Colbert from length n to length m. And the new bias, we can write it in terms of the expectation over the hyperedges and then the product of the entries. Okay, any questions? So of course, now the question is, how do we choose this hypergraph? First, I want to give you an example of choosing a random hypergraph.
Just to clarify, you're always thinking of an ordered hypergraph, right? In this.
Yeah, I think in this case, I think the ordering doesn't matter because we were taking the product.
Right.
Yeah. Okay. So that is here. Yeah. Okay. So I want to tell you an example of random hypergraph. So of course, in the end, we want an explicit construction. So random hypergraph won't work. But this will give you an idea or an intuition of why we expect such things to work. So let's choose this hypergraph to be random. Now we fix a vector x, which we assume is bias MOS epsilon naught. And then we choose a random hyperedge. So these indices I1, I2 to IL are randomly chosen. They're IID from the n vertices. And because they're IID, so each edge will have expectation epsilon naught to the power L. It's just because x1 to xi1 to xil are all independently chosen. And now we can use a Chernoff bound. We choose m random hyperedges. This gives us a bias of some constant times the expectation, epsilon naught over to the L, with probability 1 minus e to the negative m epsilon naught to 2L. So this is the error probability here is e to the negative number of things we're choosing, and then the error squared. Now, this is for fixed x. We want to union bound over all x in the base code. And the parameters here, in order for the union bound to work, we need m to be at least epsilon naught to the negative 2L times n. Okay, so let's review some parameters here. We have bias epsilon naught to the L. We're choosing this many hyperedges, which means that we are blowing up from n to epsilon naught to the negative 2L, which gives us a rate of epsilon naught to the 2L. Okay, and remember, we are allowed to choose L and we're allowed to choose epsilon naught. So if we have a target epsilon, then we just choose them so that this term equals epsilon. And then this term now is epsilon squared. The takeaway here is that bias reduction with a random hypergraph achieves a GV bound. So that's great. Even though random hypergraphs uses too much randomness, at least this gives us some intuition that this framework works. Questions so far? So the next part of the talk will be, okay, we cannot choose a random hypergraph, so what should we do? And this leads us to expander walks. Here we first pick a deregular graph G on m vertices. Our hyperedges are going to be all length L walks on this graph. So we pick a starting vertex I0, then you take L steps, I1, I2 to IL. And that's it. This is our hyperedges. The new bias, we can write it as the expectation over the walks, and then the product of these entries. Let me first give you some high-level intuition. The intuition is that if we choose G to be an expander, then at a high level, the walk will roughly go to random vertices, or random locations. And in that case, perhaps a random walk here behaves like a random hyperedge. So that's maybe the rough intuition of doing this. Let me first start with the simple case L equals 1. Yes.
So, okay, sorry, maybe I'm jumping ahead a little bit, but I know that expander walks kind of don't give the optimal rate.
Yes.
If instead of an expander, I actually picked a random graph, do you know if it would give any better rate? I mean, still not as much randomness as the random hypergraph. But
yeah, okay. So there are two things. One thing is you can take L equals 1, and then like recursively.
Okay, yeah, I guess L equals 1 is enough. Yeah.
Using different random graphs, and then the unit bound will work out.
Right. That's true.
If you choose only one single random graph and then walk on it, I think it won't work.
Okay.
Yeah. So you need. I think that you need this recursive thing even for random graph. Yeah. Okay. Like Madar said. We'll see why this doesn't work later.
Sorry.
But okay. Anyway, so L equals 1. We can write the new bias in terms of this expectation over edges ij, xi, xj. The nice thing about this is now we can write this as a quadratic form. Here, the matrix A is the normalized adjacency matrix of the graph. And then the inner product here we're using is the expected inner product. It's expected over indices I, xi, yi. And notice that using this inner product, for any plus minus 1 vector, the norm is 1. Okay, because we written this quadratic form here, we can now use the eigenvalues of A. Let's look at these two terms here. The first term is because the adjacency matrix has the all ones vector as the top eigenvector. So we get this x dot 1 squared. And x dot 1 is precisely the bias of x. The second term we get a lambda, because that's that's defined to be the second eigenvalue, or the absolute value of the minimum eigenvalue. This lambda will be at most 1 whenever the graph is connected and it's non-bipartite. We're assuming lambda to be very small because we were allowed to choose an expander. Together these two terms gives us epsilon naught squared plus lambda. So here, the first term we get, originally it was epsilon naught, now it's epsilon naught squared. That's pretty good. And for lambda, we can choose a graph that has very, very small lambda based on expanders that I'll talk about later. So there's a trade-off between lambda and the degree. But the takeaway is that we can choose lambda to be small, and then this gives us epsilon naught to epsilon naught squared. So now let's look at L steps. And this is the new bias, the expectation over all that walks. I'm going to write this also as a quadratic form, which looks like this. This is the quadratic form of the all ones vector, and then dxa, dxa, dxa alternatively. Here, dx is the diagonal matrix with the x1 to xn on the diagonal. So I'm not going to write this out explicitly. This is a very straightforward calculation. You can represent the new bias. You can represent the expectation over the walks as this quadratic form. It's dA, dA, dA. You can even write this more succinctly. This is the quadratic form of all ones, and then d, a, d to the L. Now the question is, how do we analyze this? In order to analyze and bound this term, we need to know how do the vectors evolve when they get multiplied by a or dx. Okay, so this leads me to something. I'm going to draw a diagram of vector evolution. But first, I want to make a simplification. Let's assume the bias of x is 0, so it's orthogonal to the all ones vector. So actually, this is not much of a simplification. When we are thinking about this problem, we always assume this, and then we add it back later. So for this I only assume that it's orthogonal to all ones. Now we're just going to have two subspaces, the all ones vector and then the orthogonal subspace. What happens when we multiply it by dx? Well, the all ones vector gets mapped to x, because remember dx is the diagonal matrix of x. And then for the orthogonal subspace, we don't know what happened. But for example, this can go back to the all ones vector because, for example, dx times x will be exactly all ones. So x is orthogonal, and then when multiplied by dx, it goes back to all ones. The next step is A. What happens here? All ones gets mapped to all ones because that's the top eigenvector. For the orthogonal subspace, so for any vector v orthogonal to all ones, we have that AV is still orthogonal to all ones, and then the norm gets multiplied by lambda. So here, orthogonal stays in the orthogonal subspace, and then gets a factor lambda. That's it. That's the diagram that we're gonna use. And dA. This is the diagram here. Okay, so what if there's some bias? We're just gonna add some lines here. But for this talk, we'll assume those don't exist. Okay, great. So in this diagram, we think of some edges as good. So this is good. It gets a lambda factor decrease. Lambda is very small. On the other hand, these are bad. These are in the all ones component, and it doesn't get any factor decrease when multiplied by A. All right, so using this diagram, we're able to kind of just read out the analysis. So here's a claim. We can use it to visualize the analysis. So here's a claim. Claim that the operator norm of dA is at most lambda. And importantly, this is not lambda squared. We have two A's in the matrix, but only one lambda. It turns out this is actually pretty bad. So this is a phenomenon where we get one lambda every 2 steps. And we can exactly see it in this diagram, specifically in this highlighted path. Here we have 1A, and then it goes back to the all ones component, and then it doesn't get any factor decrease in the second A. Any questions about this diagram? And, okay, in particular, this highlighted path can occur, for example, when AX is roughly an eigenvector of X. So if AX equals lambda X, then we can kind of see, let's see what happens here. All ones gets multiplied by dx and becomes X. When we multiply by A, it becomes lambda X, roughly. But lambda X and multiplied by dx becomes the all ones vector. So it goes back to the all ones component. And this is the bad path. That's not good for us. Okay, but still, let's see what parameters this gives us. So the previous claim implies that the operator norm of dA to the power L is at most lambda to the L over 2, and this is not lambda to the L. So we use this to bound our new bias. The new bias, this quadratic form, and we can bound this using the operator norm of the matrix inside. And this gives us lambda to the L over 2. And this holds for all vectors in the base code. So this is the new bias this is the bias of the new code. Let's look at some parameters. G here we picked it to be a D-regular graph. We know that the optimal lambda here is 1 over root D. This is what's known as the near Ramanujan graphs. These graphs have been very well studied. We know that for any D-regular graph, 1 over root D is the best possible lambda. And we also know many good constructions for these. Okay, and so the bias is lambda to the L over 2, which gives us D to the negative L over 4. What is the rate? In order to study the rate, we need to know how many walks we have. We have n number of starting vertices, and then for each step we have d choices. So in total we have n times d to the L many length L walks. This gives us a rate of d to the negative L. Okay, now we set this the bias to be our target epsilon, and we can see that our rate is epsilon to the 4. So unfortunately, bias reduction using expander walks, and particularly using this analysis, does not achieve the GV bound. Let me pause for questions. Now, let me talk about our construction, which is what we call free expander walks. Let's first look at what the problem was with expander walks. The problem is this highlighted path. And in particular, we are not happy when AX is roughly lambda x. So what can we do? Well, what if we just choose a different graph? Then this x will no longer, maybe this x is no longer an approximate eigenvector. The problem is that if we choose a different graph, then maybe another vector in the base code is bad. And we need this to be good for all x in the base code, so this probably won't work. What if we choose many different graphs? Remember in the previous expander walk, we're walking on the same graph. Every step we take is on the same graph. If we have different graphs, we're allowed to take each walk using a different graph. And this is exactly what we're going to do. Walk on different graphs. Suppose we have graphs A1 to AL. They're all d-regular. And then we can take the first step according to A1, second step according to A2, and so on. By the way, I'm using A as the adjacency matrix and also the graph. But these are the adjacency matrices. It's going to be the same diagram as before, but now instead of dA, 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 we have dA1, dA2, dA3. So now the question is, can we still have this bad scenario where we get one lambda every 2 steps? And this highlighted path, is it still there? Okay. Here's intuition. We're still not happy if for most graphs we have AJX is roughly lambda x. The thing is, if this happens, then we know that these matrices roughly share a non-trivial eigenspace. We know that they all share the all ones eigenspace, but if this happens, then they also roughly share a non-trivial eigenspace. And this should not happen if we can choose A1 to AL that look pseudo-random. And at a high level, it kind of means that for any x, most AJs are good. So let me say a few words about this. Look, what does look pseudo-random mean? Here, this is what we call free expanders. So actually, freeness is some formal definition, and there's a very well-studied field called free probability. Today, I won't talk about any of that, actually, because all we need is actually a specific condition on A1 to AL. That's all, and you'll see that later. That's all we need. So let's try to make this formal. Try to formalize what does most AJs are good mean. So let's assume that we have d-regular graphs A1 to AT. And then we are looking at this contribution from this bad path here. The contribution from this path can be written as the expectation over J. So we want to say that most AJs are good. But let's say they're good on average, and then we can use a Markov inequality later. So we're taking the expectation over these graphs J. And then we're looking at the contribution. If you take one O1 vector and then D, A, D, and then go back to the O1 vector. So this is the absolute value of this quadratic form, 1 and dx, aj, dx, 1. This is a quantity that we would like to bound. If we can bound it, say that this is small, then we know that the contribution from this path is very small. The naive bound here is lambda, because we get one lambda factor here. But this is not good enough, because we know the next step, we won't get any improvement. We will get a 1 there instead of lambda. So we want to really beat this naive bound. Okay, so let's do some calculation. First, I'm going to write the absolute value in the expectation as a sign. So here we have max over the signs plus minus 1 to the t. And the expectation of over j, and I'm replacing the absolute value by this sign sigma j times the quadratic form. Okay. And I will push the expectation in sigma j inside the quadratic form. So the max of sigma is still outside. And now there's a matrix in here. It's expectation over j, sigma j, aj. I'm just pushing expectation and sigma j into the quadratic form. And then the next thing I'll do is just bound this term by the operator norm. Okay, so now, so technically we can add a perpendicular sign here. And this is because the aj perpendicular, well, because we assume x is orthogonal to the O1's vector. So let's just add this perpendicular sign. This is just by removing the top eigenspace. Let's try to understand this quantity a bit better. What is this quantity? Here. So suppose that we set sigma to be the O1's vector. What do we get? We get that the expectation over j of aj is the normalized adjacency matrix of the union of these graphs. And because each of them is d-regular, the union of the graph is t d-regular. What we hope is that the union is also Ramanujan, which means that the operator norm here is at most 1 over the root degree, and degree is td, so this is 1 over root td. So we want that, so they're all Ramanujan, and then the union is also Ramanujan. We want something more than this. We want that if we have any signs here, then the expectation over sigma j aj is also bounded by 1 over root td. This is actually the precise condition we need for the A1 to AT. Any questions about this condition? Of course, the question is, do they even exist? And also, how do we construct them? Fortunately for us, this is already done before. We're just gonna cite some existing results. This is a result by O'Donnell and Wu in 2020. They showed that for all t and d, there exists an explicit construction of d-regular graphs A1 to AT, such that each of them is near Ramanujan. So the lambda of these graphs is at most 1 over root d. And then we have this sign, this property that the expected sign adjacency matrix has operator norm at most 1 over root td as well. And in particular, this term equals lambda over root t. But actually, if you go look at this paper, their result is way more general than this. But this is the only thing we need here. Okay, so now let's get back to eliminating this path. This is the quantity we would like to bound. And we already saw that this is can be bounded by this sign operator norm. And in particular, using the O'Donnell-Wu result, we know that this is at most lambda over root t, which beats the naive bound by a root t factor. And because we can choose t to be a lot larger than d, then this is much smaller than the naive bound. Okay, any questions? So basically, this is we've basically fixed the 1 lambda every 2 step problem. Are we done here? Okay, not so fast. We fixed this path. We showed that the contribution from this path is very small. What about this path? This path is also bad because here we get 2 lambda every 3 steps. Here we have lambda, lambda, and then it goes back to the all ones. The next step gives us a 1. 2 lambda every 3 steps is still won't give us the GV bound because it gives us a bias of lambda to the 2L over 3. So we also need to eliminate this. But we can again write this contribution in terms of this quadratic form. Now we have the average over J1, J2, and it's 1 and then dA, dA, D1. This is just following this path here. And actually, we want to fix this path to be within the orthogonal subspace. So we're just going to add projection operators to the orthogonal subspace in here. So this is I think this is more of a technical detail, but this is the precise bound we prove in our paper. Okay, so we want to bound this. Again, the naive bound is lambda squared because we get 2 lambdas here. And we don't like this. We want to beat this. The way we bound this quantity is, first, we just treat this term, highlighted term here, as a vector y. And because of the projection operator in here, y is orthogonal to O1s, and then y has norm at most lambda. This lambda here, we're just using the naive bound. That there's an A in here. Okay, and then after this, we just do the exact same thing as we did before. We say that this is at most the lambda over root t times the norm of y. This is, after we just treat this blue box as y, we do the exact same thing, and then we get this. And then the norm of y is at most lambda, so we get lambda squared over root t. Cool, so we also managed to beat the naive bound.
Actually, so if you take the expectation over J1 inside, so we have expectation both over J1 and J2, right?
Yeah, I skipped a detail here. I'm only using the randomness of J2 here.
Yeah. But somehow, if you also use a J1, it doesn't give you an extra root t.
We think it'll be better, but we don't need it.
Okay.
Yeah. I think it should work. Yeah.
Okay.
But we don't really need it. Yes.
But t will be much smaller, so this 1 root t is enough.
Yeah, we actually only need t to be d squared, or like d to the power something. So, and this will work already.
Okay.
Cool. Yeah, to say a few more words. All we need is that we beat the naive bound by like a d squared factor. So this is enough. Yeah. So actually, for longer sequences, we also only use the randomness of the first entry. Yeah. Okay, so this is the quantity we bound in our paper. It beats the naive bound by root t factor. And that's great. That's good enough for us. So once we do this for basically all such bad paths, there are not too many of these bad paths, so we can just do a union bound here. And so I won't go into the details there, but here's our final expander walk. Okay. So we are able to show that for fix any vector in the base code, most sequences of the graphs are good. And precisely, we mean that when we take the probability over J1 to JL, we choose these graphs at random, the sequence AJ1, AJ2 to AJL is good for X. And this is just by a Markov inequality. This is at least 1 minus t to the negative 1/4. This t to the negative 1/4 comes from that we get an 1 over root t in the expectation. The weird thing about this is that which sequences are good actually depend on X. So we cannot just pick one because some X might be bad. And we also don't know which sequences are good for each X. Well, we just take all of them. Let's just take every single sequence and t to the L. But here's an example. T equals L3 and L equals 3. The sequence of graphs will be this. We just take every single sequence and we stack them together. Okay, 1, 1, 1, 1, 1, 2, all the way to 3, 3, 3. This is our final expander walk. And okay, so let's look at the bias here. For any x, we know that 1 minus little o of 1 fraction of sequences are good. Here, little of 1 is roughly the 1 over t to the 1/4. So we're going to set that to be something large. For most of these sequences, we get a factor of lambda to the L. So the final new bias is going to be lambda to the L, and then there is 1 minus O little of 1 times t to the L good sequences. So we get this factor as our new bias. And now we plug in lambda to be 1 over root d, and this gives us d to the negative half L times t to the L. And there's a 1 minus little of 1 here. What about the rate? Or how many walks are we choosing? Okay, so in total we have t to the L sequences, which means we're taking L times t to the L many steps. So in total, we have n starting vertices, and every step gives us d choices. Remember, every graph is d regular, so each step gives us d choices, and then this is d to the L times t to the L. So this d to the L times t to the L t to the L is the blow up of our code, and we get rate d to the negative L t to the L. Now let's look at this. Again, we are able to choose d, L, and t to match our target epsilon. Then rate is epsilon to the 2 plus little of 1. Okay, so that's it. That's our construction, and that's actually most of the analysis. Yep. So I want to end with just a quick conclusion. Basically, all we're doing is we're staring at this diagram and looking at what is the bad path that we would like to eliminate. And in order to eliminate these bad paths, we use these free expander walks. The only condition we need is this fact. And fortunately, we already have constructions that gives us this. This is from Odano Wu. And that's it for my talk. Thank you very much.
Questions for Tim? Well, last one more.
Yeah.
If this t to the minus 1/4 in this probability of a walk being bad was t to the minus L over 4, then this little o of 1 would improve, right? It's,
okay. So that's a very good question. Actually, this little of 1, the dominating term of that little of 1 actually comes from, it's very weird, but it comes from lambda being 2 over root d instead of 1 over root d.
Oh.
It's not really about this little of 1 in here. This 2 here, that 2 here will give us a 2 to the that thing. That's actually the dominating term for epsilon to the in the epsilon to the little of 1.
Nice.
Yeah. So that's why we didn't bother
Optimizing this
optimizing that because
okay, I see.
Yeah.
And maybe as an aside, but the constant 2 in Ramanujan bound, is it also related to the constant 2 in front of epsilon square log 1 over epsilon that you mentioned earlier? It's
Epsilon. Oh, you can use
the
epsilon.
upper bound on the rate. There is a constant 2 there also, right? It's
no. So
these are not
no,
related.
I think these are not related.
Okay.
Yeah, I can say a few more words about this too.
Yeah.
So Gil Cohen and his students,
Uh-huh.
I think they've been also trying to construct these for some time. And they did focus on, they have a paper focusing on how to get rid of this 2. So this is something called a rotating, what they call rotating expander, where if you take an adjacent matrix and power it up to the power L, you get 2 to the L. But if you take, they show that there exists some permutation matrix you can stick into the walk, so that A pi, etc. Instead of 2 to the L, you only get L. So it's unclear how to use that at the moment, but this 2 to the L factor is something that is a problem we face, and also what people have tried to eliminate. Yeah.
Yeah, actually, even the O'Donnell-Wu expanders have this property that if you multiply them, you get like L instead of 2 to the L. But okay, I guess the issue here is just taking this dx in the middle, and then that like throws everything off.
I see. Okay. More questions? Let's thank Tim again.
Thanks for coming.